Okay, so quadratic functions have this general form a times x minus h squared plus k. But if we're looking strictly at the parent function, I want you to notice how it is in general form. It's just that it has zeros in certain places, right? So would you agree that if I were to rewrite the parent function to look more like general form, that it would be f of x is equal to x minus 0 squared plus 0? Right? Do you see how that right there is representing the parent graph as well? Right? Because it has 0 for h, which means it hasn't shifted anywhere left or right. And then I have a 0 for k, which means I haven't shifted up or down at all. Right? And we know that the standard kind of number for a is typically a 1. Right? It's an invisible 1 that just kind of hides right there in the position where a would be. All right. But if I were to clean it up, you can see how I don't need the zeros. And then that's how I ultimately end up with this parent function, which is just x squared. Okay. So I want to go ahead and graph it. And now looking at the general form, I can see where my vertex would be on this quadratic, right? I would look where my h value is, that's a 0. I would look at my k value, that's also a 0. So then I would start to want to create a vertex, and I would put that in the center of the t-table. Right, so I have 0, 0, okay, which means that I have a vertex right here at the origin. Okay, and just like we did with absolute value, when we want to graph by hand, what we would want to do is identify points that are a little bit smaller than 0 and a little bit bigger than 0. So we can use -1 and -2, as well as +1 and +2. All right, just to see where the points are going to land. All right. Now, not only that, one thing about quadratics and parabolas is that they're also symmetric, just like absolute value, right? So you can see that there's a lot of connections between absolute value and quadratics. And so what we'll see in this t-table, we'll see a pattern. We'll see a pattern of outputs, okay? So if I want to plug in my values here, -2 into the parent function, then it's simply going to be -2, and then I square it. I would take -1 and square that. I would take +1 and square it, and then I would take +2 and square it. Okay. So what I have here is, since I'm squaring -2, that's why I've put -2 inside parentheses. And although it seems like a small detail, it's a big deal, right? Because if you take -2 inside parentheses and you square that, well, what you're saying is -2 times -2, right? Negative times negative, that means we're going to get 4 as a positive, right? +4 as an output. Okay. Same thing happens here with -1 squared. -1 squared, -1 times -1, that's a +1. We already have the output for 0. It's just 0. 1 squared is 1. 2 squared is 4. Okay. So you see that there's a little bit of a pattern there with the outputs, and that pattern results we get a pattern as a result of the symmetry of the parabola, right? Which means that the outputs we get on the right side are going to be the same outputs we get on the left side of the vertex. All right. So if we go through and we want to graph these points, well, I would have a point at -2, 4. I would have another one at -1, 1. 0, 0, which we've already graphed. 1, 1, and then 2, 4. Okay. So then let's go ahead and plot everything. So we have -2 up 4. -1, 1, +1, 1, and then +2, 4. Okay, so remember that the quadratics create parabolas. Parabolas are smooth U-shaped curves, okay? So smooth, a U-shaped curve. Okay, and I'm just emphasizing that because we've spent so much time doing absolute value that I don't want you to think that you're going to draw a straight line through these points. Even if you wanted to, you couldn't, right? If I drew a straight line through this point, there's no way I'm going to be able to touch the point up here. And then if I try to draw a straight line through these 2 points, I'm going to miss this one, right? So drawing straight lines between the points won't happen, okay? So we're going to have to go ahead and draw the curve right? By hand, as best you can, nice and smooth between those points. Okay, and there's our parent function, right? So there's our original parent function quadratic. And then any other quadratic will be a transformation of this one, right? So it's still possible that we could have shifting left and right, shifting up and down, translations, or I'm sorry, reflections over the x-axis, reflections over the y-axis. We could have vertical stretch or vertical compress, right? So the same types of transformations that took place on the absolute value function can happen on this function, which is the parent function of the quadratics. Okay. Now, as we move forward, I'm not going to have you do the t-table every time. I'm going to show you a pattern that can help you graph this a little bit faster, okay? And we'll talk about that pattern when we get there. All right, any questions so far? Okay, the other thing I want to discuss is the domain and range of these functions, right? And so we haven't really talked about domain and range in a while because we haven't done graphing in a while, but I want to talk about it because every function has a different different kind of relationship in terms of its domain and its range. So I got a question. What does the f of x equal 1? Okay, so what I was trying to show you here is that the parent function x squared is the same thing as this one. Because I have a 0 for my h, I have a 0 for my k, right? So really, if I have a bunch of zeros there, I don't even need them, right? So if I wanted to rewrite it in a cleaner way, this would be the clean way to write it. It would just be x squared. But I wrote it in that general form to show you where the vertex comes from. And then I also put the 1 in front to remind you that there's always an invisible constant of 1 there if you don't see it. Okay. I hope that clears it up. All right. And so I want to talk about the domain and the range here. And now one of the things about quadratics is that they are they're a little bit tricky to imagine, like zooming out, right? But I want you to think of this as a curve that is opening up and it's getting wider at the top, right? So as it's opening up, it's starting to get wider, almost like a bowl, right? Like a cereal bowl, right? Like as it comes outwards, usually your cereal bowl is much wider at the top than it is at the bottom. So a parabola behaves in a very similar way. Now, why do I mention the cereal bowl? Well, it's because if you imagine that this bowl continues going up forever, the curves are moving up and to the left forever. And the other side is moving up and to the right forever, right? Now, when I mention these words, like moving in these directions forever, right? It's kind of a key, kind of a hint to what our domain and what our range might look like. All right. So I want you to think of the domain. Remember, it's how far left and how far right does the function go. Okay. So if we're thinking about the left side of the graph, I want you to think about just this piece here. Now, primarily it is moving up, right? But consider where it started from the vertex. It's moving up, but also it's drifting to the left, right? And it's drifting to the left and there's nothing that's going to be able to stop it. So as this function, not only as it moves up, it's moving to the left, how far left will the graph be able to go? Yeah, we're thinking here that the domain is going to take us all the way to negative infinity. All right. Yeah, and then it behaves the same way on the right side, because on the right side, it's moving up, but it's drifting to the right forever as well, right? So it's drifting and then there's nothing there that's going to be able to stop it. So then similarly, the domain, it's drifting right, it's going to carry on to the right forever. So on our domain is going to be negative infinity to infinity. So that's great because with quadratics, guess what? The domain is also negative infinity to infinity for every quadratic, right? Another way to say that is all real numbers for the domain. Okay, so that's where absolute values, functions, and quadratics are so similar in that they have the same domain, right? You can plug in any number into the function and you will generate an output. There is no number that is restricted from being part of the domain. So any number exists as a domain for this function. Okay, and that's really easy to remember now because it's like, okay, the domain for absolute value is all real numbers. It's going to be the same thing for quadratics. Okay, and that's the best part, right? So it's easy to remember. The range also behaves in a similar way, right? Remember that when we talked about range, how would we read it? Would we read it from bottom to top, or would we read it from top to bottom? Minimum to maximum or maximum to minimum? Does anybody remember what we would do? Yeah, it's bottom to top, right? It seems kind of strange, but we're kind of scanning the graph. Like, what was the minimum value and where did it hit the maximum value? So in this case, for us, we're looking at the range, and I want to say like, okay, what is the minimum y value that exists on this function, right? And what would that be? What is the minimum y value? Yeah, it's here at 0, right? Right here at this point, that's the lowest y value that we get. So we can say that it starts at 0 and we include 0. Okay, we include 0 because that's the actual point, right? It's a physical filled in point. So we can include it. So we use a bracket. And now you can focus on the direction of the graph as it moves up, right? So the range is saying, well, starting from 0, if I move scanning upwards, right? There's nothing to stop the function from continuing to go upward. So then we can say that it's going to reach positive infinity along the y-axis. Okay. So far we've seen, okay, this is the general shape that we should have. We see how the parent function behaves, right? We have the t-table, and now we have domain and range. Okay, so we're going to just continue. We're going to continue with similar types. So we would only do the bar for this type of graph. What do you mean the bar? You mean the t-table with the range? I don't know what you mean by the bar. You mean the bracket? Okay, the bracket only goes around a value that you actually have a point at. So with domain, we don't include brackets typically because you're talking about infinity, right? So you can't really capture infinity, so that's why we don't use brackets. With range, for the most part, one of those sides will have a bracket around it because the point exists on the function itself. It's a filled in point, right? So it's a closed circle. So yeah, you would use bracket at least on one of them. I think that answers your question. Okay. All right, now let's move on to a different type of quadratic. Okay, for the next function, we're going to take a look at a couple of things. We're going to talk about the transformations first. We're going to try to identify a vertex, and then we'll look at the pattern, the shortcut that allows us to graph these quadratics pretty quickly. Okay, so I want to start here with transformations. So I want to describe them the same way that we describe them for absolute value. Right? What could you tell me about the types of transformations that exist about this function right now? All right, good. We can start there, right? Remember, we always want to start with talking about the horizontal shifts. Okay, so that's a good place to start. Horizontal shift. 2 units. And remember, it's always the opposite right? So if you see a +2, you got to think, okay, it's actually not +2, it's -2, left 2, right? So 2 units to the left. All right, what about the second transformation that exists on the function? Okay, so let's talk about it. If the A value is 1, is it a stretch or is it a compress or is it neither? It's neither, right? Or neither. Because if my A value is 1, nothing has been changed to the parent. There has been no change from the parent graph because the parent graph also has an A value of 1. So there is no stretching, right? Because you can't stretch something by multiplying it by 1 because it stays the same. And you can't compress anything by multiplying by 1 because it stays the same. So when there is no different value, if the value is just 1, you don't discuss the stretching or the compressing, right? It's like that transformation never occurred. Okay. So then since there was no stretching or compressing, what else do we look for? Correct. We don't talk about the reflection either because there is no reflection, right? So in this case, there's only 2 transformations and some of them we just skip because they don't exist on this function. So then what would be the other transformation that we discuss? Yeah, we can say that there is a vertical shift 5 units. And remember that this is our K value, so that's what we keep, right? So in that case, if I see a -5, we're shifting 5 units down. Okay, so those are my transformations. So then at least I have an idea of where my vertex is going to be, right? So where is my vertex? Yeah, we want opposite and keep. So opposite would be -2, keep is -5. So I have a vertex at -2, -5. So go ahead and put the point and label it as your vertex. -2, -5. All right, now time for the shortcut. Okay, now the shortcut seems kind of random sometimes because you might be wondering like, where did it come from, right? The shortcuts come from somewhere, but where did they come from? So I'm gonna take you back to the parent graph and I'm gonna show you that there is some pattern that does exist, okay? All right, I want you to think about starting from your vertex, right? Starting from the vertex, look at the pattern that you see along the X values. You go from 0 to 1, and then from 1 to 2, right? And then we could have gone to 3 as well, right? So then you just keep adding 1. Along the Y value, I want you to see the pattern that exists. You go from 0 to 1, then you go from 1 to 4. So you add 1, then you add 3. Now think about what would happen if you would have taken 3 squared. You would have 9, right? So then to get from 4 to 9, you add 5. Right. So what do you think the next step down would be? Let's say now you had a 4. You got 4 squared. Yeah, right? You're going to add, well, this becomes 16, so then this becomes +7. So you see the pattern that has been created. It's for every X value you move over, first you add 1. Then you move over 1 more. Then you add 3. Then you move over 1 more. Then you add 5. Then 7. Then 9. Then 11. Then 13, right? So it is a pattern of where you're adding 2 each time. Okay? So the pattern occurs In this way, 1, 3, 5, 7, when the A value is 1. Okay, that is the standard pattern. When the A value changes, sometimes the pattern will double or it will triple. Right? So if A became 2, we would have to double our pattern. If the A value became 3, we'd have to triple our pattern. Okay, but for now, because the A value is 1, the same way that it is 1 in this example, then the pattern is just going to be 1, 1, 1, 3, 1, 5, 1, 7 if we can fit it. Okay, but we probably won't be able to fit it. All right, so let me show you how this works. Okay, so 1 represents, this basically represents the change in the X. This one represents the change in the Y. Okay, so then let's take a look here. Here's how you can plot it quickly from the vertex. So starting from the vertex, you're gonna go over 1 to the right and then up 1. And that'll be your first point, right? So we've taken care of that pattern. Then you move over 1 to the right, and now you're gonna go up 3. So now I've satisfied that pattern as well. Okay, I can do it probably about 1 more and then that should be enough. Okay, but typically like this is enough information right here to be able to draw a parabola. Okay, but I could do with the pattern 1 more. So you see I go 1 unit right, so it's always just 1, just 1, just 1, but then the Y value is what changes. So now instead of going up 3, now we go up 5. So 1, 2, 3, 4, 5. And then I put a point right here. Okay. And guess what? The parabola is symmetric. So the same pattern that you followed going to the right, now you do the same thing going to the left. So 1 unit over, 1 unit up, 1 unit over, 3 units up, 1 unit over, 5 units up. All right, and so we've satisfied that pattern. Obviously, we're not gonna be able to fit this one. This is overkill right here at this point. We don't need to go up that many. That's too many points and it probably won't fit on your page. So there's my parabola, right? So from there, just connect from my vertex, take the curve right through the points, and then I can erase all this other stuff here just to clean it up. And then same thing on this side. And there you go. Okay. So the pattern when the A value is 1, this is the traditional pattern right here. Okay, when A is equal to 1. Okay, the only time it'll change is if the A value is something else. So if the A value was 2, let me just talk about it real quick. Then the pattern would still be 1, 1, and 1. The only difference is that your Y value would get multiplied by 2. So it'd be 1, 2, 1, 6, 1, 10. Right? So the only change that occurs is when the A value changes, obviously it's because you're multiplying by a larger number. So the Y value grows faster, right? So instead of just going up 1 unit, you're going up 2 units. Instead of 3 units, you're going up 6 units because you're doubling that value every time. But the X value that it changes by, it's just 1 by 1 by 1. The Y value is what will stay. I'm sorry, the Y value is what we will change. All right. Do you guys follow the pattern? We'll see an example when A is 2. For now, we're just gonna kind of work with A being 1. But that's our pattern. Okay, 1, 1, 1, 3, 1, 5. Okay, and we'll talk about this in more detail later. Okay, so that's how you can quickly graph a quadratic without having to make a t-table, right? And so we just kind of want to get through this quickly so that we can see the transformations, we can see how the function has been changed from the parent graph. We can quickly sketch it out, and then this will then help us identify a domain and a range for our graph. Okay, so let's move on to that part. Okay, we talked about domain in the previous example. Okay, what do we know about the domain of a quadratic? It's all real numbers, right? So you can either describe it using interval notation, or you can give me the shorthand notation for all real numbers, which is the double R. Okay. All right, now let's talk about range. All right, we mentioned that in the previous example that range is from minimum to maximum. What is my minimum Y value for this graph? Where would my range begin? Yeah, so the range begins at -5, right? You can see here how, okay, -5 is the lowest Y value that we have, or the minimum Y value. So from -5, and then because we actually have a point, we can use a bracket, okay? And where is my range headed to? Yeah, we got positive infinity. There you go, right? You just follow the direction of the arrows. So you follow the arrows, that tells you where the range is headed. It's headed towards positive infinity. Okay, so there are the three parts of being able to do this, right? You have your transformations, you plot your graph quickly using your pattern, and then you find domain and range. Okay, any questions so far? Okay, I think we're good. All right, let's talk about another little example here. All right. So first things first, let's talk about those transformations, right? We describe the transformations, we get a better idea of what this graph is doing, where it's headed, where the vertex is, all that good stuff. Okay, so here we go. Let's start with transformations. All right, what would be my first transformation for this function? Yeah, you guys are on it. Horizontal shift. 3 units right. Okay, it's the opposite of the sign, right? So the sign was negative, that means we go opposite of that, we go to the right. Okay, second transformation. So again, same question. If you can you compress if you multiply by 1? No. So sometimes you won't have to mention any compression or stretching. In this case, although I have a negative in front, there is no a value besides 1. So then I don't describe the stretching or the compression. Okay, so you can just skip that. We move on then to the next type of transformation, which is the reflection, right? The negative that is in front indicates a reflection across the x-axis. So then that kind of gives me an idea of where this parabola is headed, right? It got reflected, so then my U shape got flipped upside down, and now it's going to open downwards. Okay, and then finally, what else can we say about this function? Yeah, we have a vertical shift, 3 units up. Right, looking at the k value. All right, so then where is my vertex? It's going to be at 3, 3. That's right. Okay, so we go 3 units to the right, 3 units up. There would be my vertex. Okay. All right, now we get to follow the pattern. The only difference now is instead of the Y value moving up, the Y value just needs to go down. That's it, right? So my pattern, remember the pattern is still 1, 1, 1, 3, 1, 5, because the A value is 1. Okay, my A value is 1. Now, because it's a negative 1, then it means, sorry, I can see how this is a little confusing. It'll be a -1, a -3, and a -5, right? Because you're moving in the downward direction, right? So the pattern must move in the direction in which the graph is headed, right? So we know that it's moving downwards, it's opening downwards. So then when you plot, right, you want to make sure it's okay. I go a 1 to the right, but instead of going up 1, I actually need to go down 1. Okay, and then we go over 1, and this time we go down 3. And then one more time, over 1, and this time down 5. Okay. And then we repeat it on the opposite side of the vertex, right? So you follow the pattern to make sure that you have a symmetric parabola. So 1 to the left now, down 1. 1 to the left, down 3. 1 to the left, down 5. So I can put it -6. Okay. And then we can go ahead and draw your curve. And there is our parabola right there. Okay. Oh no. All right. So now, final thing, right? Let's discuss. I'm sorry, I should have put vertex here. Let's discuss the domain and the range for this function. What could you tell me about the domain? What do we know about parabolas? What do we know about quadratics? It's still all real numbers. Yeah, it's still going to be all real numbers from -infinity to infinity, right? The fact that it's opening downwards doesn't change the fact that it's still opening wide to the left and to the right, right? The direction of which it goes vertically doesn't change, right? I mean, it does change, but it doesn't matter for us because it's still drifting left and drifting right, and it's going to keep going until it reaches those outer limits, okay? Now, as far as the range, okay, remember, now we're reading this from bottom to top, a minimum to maximum. Well, if the parabola continues downwards forever, what's my minimum? Yeah, you want to begin with the -infinity first, right? Because that is the minimum value. So -infinity until you get to your maximum value. And in this case, you have a maximum value of 3, right? That's your y value. Okay, so 3 with a bracket, okay, to indicate that you can include that value. Okay, how are we doing so far? Any questions? How does the graphing feel? Does it feel easy to follow the pattern? Yeah, okay, good, right? So you have a shortcut for absolute value, you have a shortcut for quadratics, right? So instead of spending all this time on t-tables and evaluating, right, you can use this to just plot your graph quick, and get a domain and get a range out of it, right? Ultimately, that's what we want to do. We want to analyze functions. We don't want to spend a bunch of time graphing them because we also have Desmos, right? And Desmos can graph it for us. So our job is more to learn how to analyze and understand where the graph will be and the orientation, the direction, all that stuff. All right, let's go ahead and move on to the next one. Here we go. And then let's see how this, how these transformations affect our graph. Okay, so let's start there, right? We're discussing transformations. What would be that first transformation that takes place on our function? Yeah, very nice, right? We start with a horizontal shift. Four units left. Okay. Second transformation. Yeah, check it out. We have a negative, but the negative is inside the parentheses, right? So the same way that when you had a negative inside absolute value, it created a reflection, but it doesn't reflect over the x-axis. This time it reflects over the y-axis, right? So it kind of reflects across this direction instead of this direction. Okay, so negative inside inside the parentheses means we have a reflection, right? Reflection across the y-axis. And then the third type of transformation, what do we see? Yeah, now we have a vertical shift 2 units down. Okay, so we follow that k value. Okay, so now let's think about where this graph is going to end up, right? Because you have your transformations, you can follow these steps. First, it shifts 4 units to the left, right? So if I was at the origin, I would have shifted 1, 2, 3, 4 units, right? I'm probably like over here somewhere. But then I reflect across the y-axis, right? So now it's going to reflect me over to the other side of the y-axis. I'm going to land, instead of at -4, I'm going to land at +4 now, right? This is like my vertex point that I'm moving around, right? So first it went 4 units left, then it got reflected, and then I want to shift now 2 units down, right? So now we go down to, this is now my vertex right here, okay? Now, why is it that it's there? This is also one of those times where you get to use keep instead of opposite keep because of the reflection over the y-axis. Having the negative there inside of the parentheses is the only time when you can use a keep for your vertex, right? So that's exactly where we end up, right? If I keep, I get a 4. If I keep, I get a -2. That is where my vertex is currently at, okay? So let me erase all this, right? So that's why we have a vertex there, okay? So the negative there only tells us about reflecting over the y-axis, okay? Out front, I don't have anything, right? In front of the parentheses, I don't have anything. It's empty, right? So it's just gonna be invisible 1. So what do I know about the direction of this graph? Is it gonna open up or is it gonna open down? Yeah, it's still going to open up, right? The A value is still a positive. So it's going to move in the upward direction. Okay. Now, on top of that, A is 1. So that means we get to use the simple pattern of 1, 1, 1, 3, 1, 5. Okay. The only thing that was unique about this one, this graph, is that we had a reflection over the y-axis, right? So it was to remind you that that can still happen. And when it does happen, it's when you use keep as your vertex. Okay. So vertex is at 4, -2. And we can use our pattern that since A is 1, we have our 1, 1, 1, 3, 1, 5. pattern, okay? So let's go ahead and plot that. So we go 1 to the right, 1 up, 1 to the right, up 3, and then 1 to the right, up 5. Okay, and then we go do the same pattern, but on the left side. So 1 left, whoops, don't want to put the point there yet. 1 left, 1 up, 1 left, 3 up, 1 left, 5 up. Okay, and there are my points, and I can go ahead and now graph the curve. Left side. Ooh, that's a little rough. Let me try to fix it. A little better, and then right side. All right, there we go. So there's my curve. Make my dot bigger. All right. Not too bad, right? Not too bad. So now let's finally discuss domain and range for this function. Okay, we got domain here, range here. Domain, nice and easy, right? We know it's always going to be the same thing for every function. What is that domain? All real numbers, right? Okay, you can indicate it this way, or you can indicate it using interval notation. Okay, there's many ways. And now the range. What would my range be? Yeah, we look at that minimum value. Minimum value along the y-axis is -2. So -2 is the minimum. What's the maximum? Well, it moves upward forever. So it's headed towards positive infinity. So there's my range. All right, so we go from -2 to infinity. Those are all the possible y values. From negative infinity to positive infinity, all my possible x values. Okay, not too bad, right? The graphing, the transformations, very, very similar to absolute value, right? So that's why we did absolute value first, right? And then we just kind of carry on what we know into the next function because it's so similar. All right, any questions so far? How are we doing? Okay, so these 4 examples, I just wanted you to get down that pattern. Okay, what I want to do next is I want to show you a couple of examples when the pattern changes slightly, right? And I kind of previewed that earlier about like what happens if A changes. Well, if A changes, then the pattern does change as well. Okay, so we'll take a look at that next. All right, so let's take a look at this function. Right now, you notice that the big change is my A value is A2. Okay, so pattern will be similar, but it will change. Okay, so this is where we got to change that pattern up by doubling. Okay, so here we go. Begin with transformations, right? Tell me what you see. All right, so we got first transformation, horizontal shift. One unit left. Okay, what's next? Yeah, now we have a vertical stretch, right? Because we finally have a value that is larger or smaller than 1. So we can now describe vertical stretch. By a factor of 2. Okay, so we're stretching out our function, our graph. It's going to be thinner, more narrow by a factor of 2. Okay, third transformation. Yeah, we have a vertical shift. 5 units down. Right? And is there anything else? We're done, right? In terms of transformations. That's it. There's only 3. No reflections, right? So let's focus on getting this pattern down correctly, all right? So the vertex, right? What is my vertex in this particular case? Got to start there. We have -1, -5, right? So we're going to go 1 to the left, down 5. Here's our vertex. Okay, here's how the pattern changes. Okay, so remember, if A was 1, you'd have a pattern of 1, 1, 1, 3, 1, 5. Okay, but this time, my A is actually 2. So the X part of the pattern does not change. It's still 1, okay? That never changes. What does change is the Y part, okay? So the Y part, yeah, this time it's gonna be 2, 6, and 10, right? And how did I get those numbers? Well, I took these values and I multiplied them by 2. Okay, multiply them by 2 because that's the new A value. So that A value is my multiplicative factor. Okay, that is the factor by which I multiply my pattern by. So that's why I was able to go from 1 to 2, 3 to 6, 5 to 10. Okay, and we should expect that. We should expect a more narrow graph because of the fact that we are stretching, right? We're stretching the graph up. So it should be moving up faster. Okay, and so we'll see that when we graph. So let's follow pattern, right? So we got 1 to the right, but instead of up 1, it's 2 up. Got my point. 1 to the right, up 6. So 1, 2, 3, 4, 5, 6. And then I'm not going to be able to plot the last point because it's over 1, up 10, and I'll be out of space. Okay, so we were able to at least do 2 sets of the pattern. That's fine. Now we go 1 left, up 2. 1 left, up 6. Okay, 1, 2, 3, 4, 5, 6. And then that's really the only way that that pattern will ever change, right? So when A changes, the pattern changes with it. So let's go ahead and graph. And there we go, right? So you can see that it is more narrow, right? It is more narrow compared to what we usually graph. It is growing much faster in the vertical direction, okay? But that's really all that'll change, okay? That's the only change that we really see. All right, so finally, domain and range. Okay, what can you tell me about domain? It's your favorite phrase. Nice and easy, all real numbers, right? And the range, the actual range, minimum to maximum, how could we indicate that? Yeah, right. Let's look at the minimum. The minimum in this case is a -5. So at -5 was where we start the range. with a bracket around it. It's a whole circle or filled in circle, and then it moves in the upward direction. So then we're going to positive infinity. And then we have our parentheses, okay? So there it is. All right, any questions?